what appears to have happened in the above reaction? Okay, we've got an alkene. What else? You're saying a substitution reaction? What was your substitution?
The bromine is gone.
So really by saying substitution, you're saying loss of bromine,
Yeah.
okay, or loss of your leaving group.
And you added more carbons to.
Okay, so maybe what we should do is highlight the atoms. Where are those carbons? That's a bad color to pick. Let's do this color. Where are those carbons in your product? Got rid of those carbons. And I got rid of them, but connected them to those carbons. So we lost bromine, so that would suggest a substitution that we would have to have replaced with what? If it's a substitution, leaving group leaves, what replaces it? The nucleophile. What charges the nucleophile? What charges a nucleophile? Negative, because it's sharing electrons. So the atom that is nucleophilic would be where? Probably in the blue structure, right? Does anybody see a nucleophilic atom in there? Nucleophilic carbon? If anything, what do you see? An electrophilic carbon. We have a positive carbon at that carbonyl. And yet for this reaction to occur, I need to have a negative carbon. Right? Well, maybe I've got an enol thing going on, right? And I could remove the hydrogen there at the alpha position. Okay? That could have worked, okay, to at least match up. But if I removed that, I would have needed to have reacted the carbonyl with the base first. Did I do that? No. Okay, so this is kind of weird. I've got an electrophilic carbon that is somehow nucleophilic in the case of this reaction. Okay, that's kind of weird. Okay. Or maybe we're looking at it wrong. Maybe this is the nucleophile. Does that make any sense? No, bromine's the leaving group. It would take the electrons. That doesn't make any sense for that to be a nucleophile. So I am somehow taking two electrophiles, mixing them, and they are now forming a bond between them. What the hell? This is really bizarre. Okay? So within this process, we need to be able to address our nucleophiles and electrophiles, and we've addressed the big ones. Everything looks like an electrophile. Right? We want to be able to look at those structures and see what those things can do, and again, evaluate nucleophile, electrophile. Okay, so let's slow down and not look beginning to end. Let's just look kind of in the beginning. What do I see here? See a phosphorus. Okay, well, what's special about phosphorus? We said it could be an electrophile in the past when what? When it was connected to bromines. PBr3, PCl3. Okay, those were electrophiles. Are we connected to electronegative atoms? No. So in this case, what is that phosphorus going to be? It's probably going to be a nucleophile. And yeah, we probably are going to see a substitution. That could probably attack. Okay, what is the result of that? Right? Okay, almost. What's wrong with it? Charge. Phosphorus should be positive. Okay, does phosphorus want to be positive? No. So it would want to get electrons. If it tried to grab electrons, we'd be stealing them from the pHs. pH is a phenyl ring. Okay? Is a phenyl ring going to be willing to just have its electrons ripped away? No. Okay? So it can't take them from the phenols. If it tried to take them from that last carbon bond, well, then we'd just be right back to where we started. So that doesn't quite work. So that phosphorus wants electrons somehow, but it can't get it from the immediate surroundings. Okay, so we're kind of stuck there. What do we add in the next step? Whoops, erasing the wrong line. Butyllithium. Well, what does butyllithium look like? There's a lithium connected to CH2, 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 CH3. What's the chemistry of that guy? Where's the most reactive bond? The lithium carbon bond. Where do we expect the electrons in that bond to spend most of their time? On the carbon, because it is more electronegative. So that's a negative carbon and a positive lithium. Okay. Is carbon stable negative? No. So what is that carbon screaming to do right now? React by sharing electrons with something. Okay. If it shared electrons with the phosphorus, that becomes problematic because too many bonds. Okay. So it can't really share electrons with the phosphorus. Okay. Maybe it shares them with the carbon. Okay. If those electrons came in and shared there, we could kick out the phosphorus. Okay. Problem with that then is we've done a substitution where we've now extended and we just have a long carbon chain. And for that matter, why the hell would we do that in the first place? Why would we even do PPH3? Why not just add butyllithium right out of the gate, the alkyl halide? Okay, so it's probably not doing a substitution. What do substitution reactions typically compete with? Eliminations. Okay, but to do an elimination, we would need a potential leaving group, and that's where things get a little bit weird here. I do have hydrogens there. Why would those hydrogens be even partially acidic? The phosphorus being positive wants electrons. If it can't permanently grab electrons, what does it want near it?
Electrons.
Electrons. So if it can't actually make a bond, what is it going to do? It's going to make sure any atom around it just has more electrons. That carbon ends up being relatively acidic because I can put those electrons on that carbon and those can be partially stabilized with the phosphorus. What did that just now build, though? A negative carbon. A negative carbon that is nucleophilic. What's the last step? An electrophilic carbon. Okay? So we have this massive cascade of things that all kind of stack and contribute to each other. Okay? The end result is that we end up with this final structure. And yes, there is some stuff in there that seems a bit weird. Notice that even if it did that attack, did that nucleophilic addition, wouldn't we still expect the oxygen to be there? Okay? All we did was broke one pi bond. Where did the oxygen go? It's somehow been replaced. Okay? So we have to figure out what is happening at each of these stages and break it down. Okay? So if we look, again, really, really slowly now at our steps, we've got our alkyl halide, and we have the triphenylphosphine. Okay? That triphenylphosphine is massively sterically hindered. Okay? Which means what about the substrate? The substrate should be relatively small. Okay? That is going to be our ideal target. If it instead, ideally, I think that's what I was trying to write, if we'd instead done something like this, do we expect to get the substitution? Probably not, because now the phosphine can't attack because they're too sterically hindered. So when we're looking at this initial step, we're aiming for a sterically small alkyl halide to react with that triphenylphosphine. The phosphine can share its electrons in. We kick out the bromine, and we've done a standard substitution. Okay? What kind of mechanism would we expect here? SN1 or SN2? SN1 means carbocation. Would we expect a carbocation with a primary substrate? No. Why are you saying SN1? I think you have a decent argument for it. Why is the backside attack sterically hindered? Yes. The phosphine structure is so large that we might expect some steric hindrance from that as a nucleophile. Okay? That's why you're thinking SN1. Unfortunately, it follows the SN2 dynamic, so we get a backside attack. The phosphine does do that backside attack to form our positively charged structure. Okay? So it does follow our SN2 dynamics. Okay? So, conclusions. We want best with our primary alkyl halides. Secondary work, but they're much, much slower. Okay? And that's a steric hindrance effect. The phosphine is too large, it just can't get in there. Okay? This is really just trying to prime the carbon. It's like an activation. We added hydrogen onto our OHs to make water a good leaving group so that it could leave the structure. That's kind of what's happening here. We're putting that phosphine on to prime our carbon, to set it up to a point where it can become negative. Okay? Which does seem a bit weird here, because that phosphine is positive. Shouldn't it want to take the electrons, leaving behind a positive carbon? Okay? Well, that's how we move into the next reaction. Okay? Notice we have two boxes. Why would we have two boxes? Okay, there's two possible products because there are two possible mechanistic steps, right? We have the butyl lithium. What could the butyl lithium act as? It could act as a base, and I don't remember if this is tied correctly or not, but we'll try. It could act as a base, or it could act as a nucleophile. Okay? If it acts as a nucleophile, what happens? Well, actually, first, we see butyl lithium. We should immediately erase the lithium and put lone pair electrons down. Okay, why? Okay, that's an ionic bond. It's a metal and a nonmetal. Carbon being more electronegative than lithium should take the electrons. So I can immediately ignore the lithium. Okay? So now I have that lone pair of electrons. If it acts as a nucleophile, whoops, sorry, didn't realize where my structure was. It could do a backside attack, kick out our leaving group. Okay, the result, try and color code these. We have our 3 original carbons, followed by our 1, 2, 3, 4 new carbons. Well, the phosphine was a nucleophile at the beginning, okay? Our phosphine was a nucleophile, just like our bromide could be a nucleophile. That seems a bit weird of a reaction to run. Okay? Why not have just tried that from the outset? Okay? Could it happen? Potentially. But it again has to do something with that phosphine characteristic. That phosphorus wants a little bit more electron density. Okay. Yes, it could get its lone pair back, but it wants more than that. So, well, phosphorus can't exceed its octet. Really? Where is phosphorus on our periodic table? Third row. And what is special about the third energy level? It can exceed the octet because it's not large. There's a particular reason on why it happens in the third energy level and not in the second or the first. And it's not size. Getting at the right idea. Okay. Phosphorus has p orbitals, but so does nitrogen, so does oxygen. So I don't quite accept p orbitals. There's not any more p orbitals. There's only 3 p orbitals, period, for any energy level. What happens at the third energy level? What happens when you transition from first to second? First energy level has what orbitals? S. And first energy level has just S. That's it. There is no and, it's just S. Second energy level. S and P, which is why we then have the octet. Third energy level. S, P, D. We now have access to the d orbitals. It is only because we have access to the d orbitals that we can now expand the octet. Where is phosphorus located? Third energy level, which means it has access to the d orbitals. It can expand its octet. That's the reason we can expand. It's because we've hit that place where we have more orbitals to access. Okay? If we don't have those orbitals, we can't expand. Phosphorus can expand its octet, so it could potentially accept more electrons. However, to have that negative immediately come in and attack the phosphorus, just say, hey, have an extra bond, those phenyl groups now are so large that I can't just do the raw addition. Okay? So that step isn't valid. So where can I get electrons? Okay? If I have the butyllithium act as a nucleophile, I end up right back with standard phosphorus, still not getting its more electrons. If I have the butyllithium directly attack the phosphorus, that's sterically unallowed. So that's not allowed. What if the butyllithium comes in and removes a hydrogen? What's the result? What do we have next door? I now have a negative carbon. Okay? And if we kind of ignore all of that, ignore the phosphorus and all that fun stuff, let's say we just drew another structure. I was looking at this, and I happen to draw this structure. Is this structure a stable thing? Yes. Okay. Why are you saying yes? And everybody else said no.
You can change those charges to a pi bond. That's all.
It's just a pi bond. What's happening with our phosphorus structure? There is the potential, and this is where we have to be careful with our terminology here. There is the potential to form a pi bond there, which then means that phosphorus now has its extra electrons, okay, through a resonance structure. Okay, and we have to be careful with our wording here, and I keep saying potential. Why is it a potential? It doesn't actually happen. Well, but when they were carbons, it actually happened. So I don't understand. What do you mean, Jenna? Why does that not actually happen? Why did it happen in the first case, when they were carbons? So we could try and make an electronegativity argument. There's another one. Octet, believe it or not, isn't going to help us out here because we can exceed the octet, and the reason we can exceed it, and this structure ends up being a better structure, is phosphorus loses its charge. It becomes neutral with that extra pi bond.
Because they're close enough that the opposite charges actually...
There's getting an idea. What's close enough in the case of our carbon structure to form the pi bond? The atoms themselves, when they're both carbons, are much, much closer than if it was carbon and phosphorus. Carbon and phosphorus, the phosphorus is further away because it's a larger atom. Okay? What is making the bond between the carbon and the phosphorus, or the carbon and the carbon? the p orbitals. What p orbitals in our carbon structure? Not empty. They can't be empty. The second energy level, 2p and 2p. Okay? When we move to carbon phosphorus, what orbitals are making that pi bond? 2p and 3p. If we look at our 2p in a Newman type projection, we're probably going to see something kind of like I just drew, where the red's on top of the blue. Perfect overlap. We're going to get a really strong bond. What happens if we move to our phosphorus carbon? Now we don't get quite as good an overlap, right? Which then means no bond. Okay? So the pi bond that we're showing here helps to explain why that hydrogen is acidic. Okay? But that's all we can really use it for. Okay? The black structure is not the active structure. It's not a valid structure. It's the purple one. Okay? What is now special about the purple one? Well, it is known as a Zwitterion. Why is it a Zwitterion? Anybody know German? Zwitter? No, not ringing bells. Is twins. So a Zwitterion means twin ions. We have two ions. We have the positive and the negative. That's a Zwitterion. So when we look at a structure that has both a positive and a negative in it, we can refer to that species as a Zwitterion. We have a Zwitterion. Okay? So it gets this weird, goofy name because it's a Zwitterion. Okay? It also has this weird, bizarre chemistry associated with it because that carbon is now negatively charged, which means it can act as a nucleophile. So because of all this extra chemistry, that kind of structure, that system where we have this Zwitterion with a nucleophilic atom, gets another name. It gets the name of Wittig is the overall reaction. This is a specific piece of the Wittig reaction. The Ylide, Y-L-I-D-E. Okay, so this is the Ylide. The Ylide is awesome because of that nucleophilic characteristic. Okay, and it looks like I did draw them backwards. So we end up forming our Ylide. That is now a pretty decent nucleophile. That can be used in a nucleophilic addition, say if we moved to the next step. Okay. Everything we've talked about up to this point is fair game. You should know all of those mechanistic steps. Why might you think that we don't need to stress as much about mechanistic steps now? Come on, you can look at the slides. Why might you say, I guess we don't need to stress too much about those steps? There's two arrows drawn immediately over each other, which means we're doing multiple things in the same step. Okay? That's usually a big sign that you don't need a mechanism. What's written under those two arrows? Mechanism debate. Okay? Because the exact mechanism is not known. Okay? Under certain conditions, we see one result making us think it's this type of mechanism. When we change those conditions around, we get a slightly different result, which doesn't quite mesh with that mechanistic analysis. So we get some variations from it. Ultimately, we can look at our products to establish that a couple things happen. One, that negative attacks the positive carbonyl. That has to happen. Okay? The next part of this is that we then also have to break those pi electrons. Those electrons have to go somewhere because we have too many electrons around the carbon. Okay? Well, that would mean we'd have a negative oxygen. Okay? That's charged. And we also have a positive charge floating around. Can we kill two birds with one stone? You're taking it too literally. Okay? We can have that oxygen, the lone pair from the oxygen, come back and link back to the phosphorus, generating what kind of intermediate? A cyclic intermediate. Okay? With how many members in it? How many atoms in that intermediate? We've got the negative carbon attacked to the carbonyl carbon. The oxygen is connected to the phosphorus, and the phosphorus is connected to our original carbon. So we have 4. We have a 4-membered ring. Okay. Now we run into some fun stuff. We still have to make it out to our final product. Okay. And a lot of this has to do with the connectivity between the oxygen and the phosphorus. Okay. There is a stronger bond between oxygen and phosphorus than there is between carbon and phosphorus, which means, let's see if I screw up the arrows. Oxygen can shuttle the electrons across to make a pi bond between the phosphorus and the oxygen, but then the phosphorus is now well exceeding its octet, can't do that, so what happens? What's the result? Phosphorus takes the pi bond with oxygen, floats off, and what's left behind?
Alkene.
An alkene, a pi bond between those two carbons. Okay? Nifty little reaction for all of those little pieces. Does anybody look at that and say, oh, no, really, I got to worry about that too? Because yes, you should. What is that oh, no thing? Take a look at the product. I have my larger group on that side, I have my larger group on that side. This product is shown as trans. Didn't show the cis. Okay. Well, which one does it favor? This goes back to that mechanism debate. Okay. So you tend to not get questions about which one is drawn out. Okay. Trans tends to be more favored, but there are conditions where you can force the cis to come out. Okay. So we will get a mixture of E and Z. Why would we expect more of the E than the Z?
Trans configuration is more stable.
Right, so I asked the question intentionally, E versus Z, so we have to say E is trans, Z was cis. Trans is more stable than cis because largest substituents are as far away from each other as possible. Okay? But you do end up with a mix of both. Okay? So the big power behind this is that we can lengthen our carbon chain again. Okay? And we can lengthen it by a sizable amount depending on how long the alkyl halide is and the substitution on the carbonyl. Not only that, but when we run the chemistry, we don't lose the chemistry. We've modified it, but we keep the alkene chemistry. We can still do what type of reactions with the alkene?
Addition.
We can run addition reactions. Okay? What type of addition reactions? As a hint, we just did nucleophilic addition. We can do electrophilic addition. Because the alkene is a nonpolar bond. Right? It's going to act as our source of electrons. This is our Wittig reagent. Okay? This is what it does. You end up seeing a variety, let's see. You end up looking at a variety of different ways to represent the Wittig. Right? The first example, okay, we showed it as 3 distinct steps. We start with the alkyl halide. We add the triphenylphosphine, we add the butyllithium, and then we add our carbonyl. Right? You may also see it as, here's the carbonyl. Well, we can't start the Wittig with a carbonyl. We needed the alkyl halide to have the phosphorus attack to have the Ylide. Except what am I reacting the carbonyl with? The Ylide. So I've skipped the first 2 steps and made those into a reagent that I can now react to the carbonyl. So there's a variety of ways you can piece this together and look at it. That's what you need to be aware of when you look at the Wittig. Kind of make sense? Okay. So I'm going to draw out the first one for our cheat on how to go through and do these. Okay. I'm going to start with the carbonyl at the bottom. Okay. So in this case, there's the carbonyl. So the whole point in this, as people started to notice, is it was kind of a substitution, right? We lost the bromine and replaced it with that carbon. And then we somehow also lost the oxygen and also gained a pi bond. So we did a lot of stuff. We can't just say it's a substitution. But the overall kind of impression is that of a substitution. So draw it as such. What happened? Well, step 1, you put the phosphorus on with the intent of making it a negative carbon. What did that negative carbon then do? Attacked the positive carbon of the carbonyl, which then kicked out the oxygen. I mean, that's the answer? Yeah. Draw the carbonyl, draw the alkyl halide above, erase the halide, erase the oxygen, connect the carbons. You're done. That is now the product. Okay? So it's a very fast way to draw the answer for the Wittig reaction. Okay? So it's a nice kind of shortcut. You'll never see it drawn like that on an exam. Okay? You will see it drawn out where it's in that kind of as close to as possible straight line. So once you've done the cheat, it may not be a bad idea to find your longest carbon chain. 1, 2, that's not the button I pushed. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Between position 2 and 3, I have my double bond. I have a methyl there, and I have a methyl there. Right? Just to kind of make it look easier so that you can then see your answer on the exam. Okay? And the other part is you have to realize we might have cis-trans. Do we need to worry about cis-trans with this one? No, because
It's under debate.
nope. Even if it wasn't under debate, this one is completely irrelevant when it comes to cis-trans. There's no difference between the methyls, which means I can't star a priority for one way or another. There is no cis-trans with this product. That's why I don't have to worry about it. Okay? When you get to the exam, you have to be careful and make sure that if you're looking at multiple choice and you have a cis and you have a trans, both are valid products. Okay? Kind of make sense? Okay, so I drew the first one. You guys do the next two, and I'll redraw the first one to make it look pretty. So again, our shortcut for the second one, I need to get rid of the oxygen. I need to get rid of this phosphorus. This is my nucleophilic carbon. That nucleophilic carbon needs to go where that oxygen is located. Okay? It's not attacking the space. Okay, so that's where I got to be careful. I'm going to stop making that look like an arrow. Okay? They are connecting there. Okay, so if I draw out the ring again, double bond. Here's the carbon now, my nucleophilic carbon. That nucleophilic carbon is connected to a second CH2 and a CH3. There's my answer. Make sense? Okay. So we can kind of shortcut those steps when it comes to Wittig. Okay. Where this can become more challenging is when we move to the last one. Because in the last one, what are you being asked to do? Supply the reagents necessary to do this. Okay? And technically, I asked for two different methods. Okay? So if we know nothing else, hopefully we paid enough attention in the lecture to know that we will need triphenylphosphine. We will need butyllithium. Okay? If you're particularly lazy, you could just write BUTLI, because that is now butyllithium. Okay? We need to react with some alkyl halide. And our step 3 is some carbonyl compound. Okay. That information in and of itself should eliminate probably 2 answers in a multiple choice test. In a show your work, you have now specified some work. I can give you credit. Leaving it blank, I can't give you anything. Okay, but here you've at least established something useful. Okay, let's reverse the logic of our shortcut. In our shortcut, what did we do? We got rid of the oxygen, and we got rid of the phosphorus. Okay. So if we take a look at the structure drawn, I'm going to stretch that pi bond. Right? Didn't change the structure. I'm going to erase the middle out of it with a different eraser. And I'm going to draw on an oxygen, and I'm going to draw in my phosphorus, right? But I said triphenylphosphine, so really the phosphorus got connected to that carbon because why? The carbon was positive. Why was the carbon positive? Yes. There was a leaving group. So there we go. There's one answer. Ta-da! What's another option? Let's put the oxygen up here and the bromine down here. Oh, wait, bromine can't have that extra bond, so it's just that. So I'll take my alkyl halide, react with the triphenylphosphine to have the phosphorus do the substitution. I'll react the butyllithium to do the Ylide. I now have the active nucleophile that can attack my carbonyl as I throw stuff on the ground, and I'd end up with the final product, which we can now no longer see because I drew over the top of it. Does everybody see that? Okay. Why did I ask that question? That's a hard one.
Different ways to do it.
Okay, number one, there's multiple ways to show that we can get the same product. Cool, I like that idea. There's another one.
There's a
Is it on the
difference.
ACS?
It could show up on the ACS.
One of the top one is slower than the.
Which of the two is the best Wittig reaction? Okay. So on a multiple choice, I could ask, which of the following is the best to make the product shown? There are two valid answers, one of which doesn't work as well as the other. That reasoning comes back to how the reaction works. Our very first step was a nucleophilic attack on the alkyl halide, a substitution. A nucleophile that was insanely bulky, which means what did I want for my alkyl halide? I wanted it to be as small as possible. I wanted a primary. If I go back and look at my two reactions, I have a primary alkyl halide and I have a secondary alkyl halide. Which one reacts faster? The primary. That now becomes the better answer. Does that make sense? Okay. So lots of different little kind of niches that we can move through on this. Okay. When it comes to the complete mechanism, no. Beginning to end, alkyl halide to the final alkene, no. We won't expect you to be tested on that mechanism because we don't know how that final phosphorus oxygen structure is formed and how it decomposes. We've got good ideas, we've got general things that we can make up, but we don't know exactly. However, the first two steps, absolutely fair game for mechanism questions. They're just a standard substitution and then a standard acid-base reaction. Make sense? Okay, questions? Sweet. So, this is just talking back about the Ylide and what's going on with that resonance. We do have that formal negative charge on the carbon. We do have the potential for that resonance, and I don't remember if this slide actually addresses it or not. Nope, it doesn't. I think the intent here was really to draw attention to the fact that we really don't form a pi bond between the carbon and the phosphorus. And it's due to those uneven p orbitals, they don't line up. This does set up slightly better mechanistically, nice mechanistic curved arrows, but that's about it. Okay, retrosynthesis. Okay, we just did this. Do you want to do another one on your own, see if you can come up with it? Yes, okay. Okay, Jenna, you made a face, so I'm going to ask you. Why are you making a face? That's not true.
I think going on the left would be better, just because I don't think the phenol phosphorus molecule would want to attack another cyclic structure. But that's just you.
But that didn't sound like anything like we talked about, right? Didn't we just say we needed the least sterically hindered alkyl halide?
But they have the same.
Okay, that's where I wanted to start. Yes. So that's probably why you made a base, right? You're like, they have the same substitution. They're both secondary alkyl halides, okay? Which means they're probably both the same. But I was a jerk and said, push harder. And so you decided the one on the left because?
It's not connected to the cyclic structure.
Okay. This having free bond rotation all the way around maybe allows for a better phenyl attack or phosphorus attack. Anybody want to debate that? You just want to wait for me to debate it? That's not very fair. I don't have a debate, actually. I don't know. I think your argument makes sense. That's all I would expect out of that. Okay? I want you to be able to think about those reagents. The big obvious suggestion isn't there. After that, we're now kind of left at kind of a conundrum. We're coming up with the best option we've got. We're making the assumption that those sigma bonds are more open on the back end. They could potentially rotate cleaner away than the ring. That could make sense. You could also make the argument that because it is in a ring, those are locked permanently away from the backside, which would then favor the one on the right. Okay? How would we find out for sure? You'd have to go into the lab and test it. Okay? Only after it has been tested can we come back and say, well, this is why I'm right. This is the same deal with all the mechanisms we've looked at throughout the semester. Okay? Someone went through and said, I think this is how it's going to work. So they went into the lab, they tested it. Yep, I'm right. And somebody else is like, I don't believe you. I'm going to test it with this stuff. Oh, I got a different answer. You must be wrong. Okay? And so then they fight it out, and that's what's happening. We're trying to establish why and when individual mechanisms work. The way you see it in class is someone sat down and said, whoop, this is the answer. Fat chance. Okay? Maybe one or two reactions in the entirety. Almost all of it was an experimental observation. Remember the people that we give credit to? Zaitsev? Okay. What was the other one? Markovnikov? They didn't know what electrons and protons were. They didn't just sit down and draw this out. Okay? This was them staring at a bottle and saying, well, this is the end result that I got. Okay? Even be able to be that whole, like, you think it's that structure, but you don't understand that there are electrons. Even that kind of makes my brain go, I think you're just making shit up. But he made it up well enough that everybody else believed him. Okay? Probably because he didn't make it up. He had some evidence. Okay? But they're working at those levels. That's where all of this science is coming from. It's not someone just sitting down and saying it. They're sitting down looking at it, coming up with what aspects they're aware of. Electronic effects, steric effects, and applying what they know about those to the reactions, and then testing it. Unfortunately, you're in the boat of can you regurgitate what somebody else tested and proved. Okay? This is why organic chemistry is fun, is the thought process. It sucks to be tested on what somebody else thought about. Okay? But that's where we are. Okay? I only have this slide in here because it's an important reaction for biochemistry. Okay? You can look at sulfonium Ylides. They do effectively the same thing. It is the transfer of a methyl group. Okay? And I'm going to stop recording temporarily. It does it when it's supposed to. Okay? That's the importance of methylation. Your body can go through and methylate DNA to say, hey, there's a mistake here, come back and fix it. Okay? It can just add methyl groups onto structures because we want more carbons. Okay? If you look at fat storage, we're putting more carbons into those structures so that we have a more condensed fat structure. Okay? So methylation is an important chemistry. It typically goes through the sulfonium Ylide. You're looking at sulfur transferring those electrons, okay, or facilitating that. That is pretty much the only reason it's there. Okay? So to that end, whenever anybody says, what did you learn in OChem? You're like, you didn't talk about anything in the real world. I did. Okay? I didn't record it, but I did. Okay? That's what's happening with our sulfonium Ylides. That's what's going on there. Okay? That's really the only reason it's there, and it's in your homework because I want you to actually read it. Okay? But it's doing effectively the same thing. You still have an alkyl halide. You still have a really strong base in the sodium hydride. Okay? You still make the Ylide. Once you have the Ylide, you can then do some methylation chemistry with that. Okay? Epoxides. Okay? Again, fun stuff, more sulfonium Ylides. When you react it with the carbonyl, because it's only a single carbon, you have a leaving group in the sulfur, and you have a nucleophile, which means you have effectively a carbene, a nucleophile, and an electrophile with the same carbon. You can form a cyclic structure, okay, a 3-membered ring. That's it. Okay. Do you want more? Really, we can only do one more because the bottom one we've already done. Do you want to do another one? What are your 2 methods to make that one? Oh, that was a bit silly. Nope, you can really only do one because I'd have to erase that to get you 2 methods. What do you guys think? Are we Wittigged out? Good. I want to be Wittigged out too. Please reconnect. Okay. So our spider diagram, looking at our pieces again. Come on, pen work. So we've done the sodium borohydride, the lithium aluminum hydride, we've done the Grignard. We kind of just left the alkyl lithium floating out there, just said it's kind of there. It's the same way that you would do the Grignard. You take an alkyl halide, instead of adding magnesium, you add lithium. Lithium metal, again, doesn't want its electron, shuttles that out to the carbon structure. It does the same insertion into the bond, and we end up with the same nucleophilic carbon. Okay? And you can react that with carbonyls. So we've done that one. We've now done the Wittig. The acetylide, we've not explicitly talked about. Okay? Really the important part is within that red box is the acetylide ion itself. How do I get the acetylide? I start with acetylene, and I need to remove the hydrogen. How can I remove the hydrogen? I just need a strong base. Okay? Like what? What's a good strong base? NaOH, which unfortunately is wrong. NaOH is not a strong enough base to do this. NaH, interesting, would work. The other really common one that's typically associated with it is sodium amide. Why would we choose sodium amide over sodium hydride? Hydride is super reactive, could probably do some damage to the rest of the structure. Also, what does it produce? Hydrogen gas, which is explosive. Okay? So, yes, we could use it, but again, our target is to use the strongest thing that is weak enough to do what it needs to, or the weakest thing that is strong enough to do what it needs to. Right? Okay? So we've now covered the top part. Really all we got to move into is this now second stage. Okay? We're going to modify the carbonyl ever so slightly. Okay? We're going to take our carbonyl structure and we're going to add an extra carbon. And then that carbon is going to be connected back to the alpha carbon of our carbonyl through a pi bond. So we have an alkene. What is special now about this structure? For those of you following along at home, we're looking at the blue box. Why was the carbonyl reactive? So we'll now go up to the purple box. Carbonyl is reactive because it is electrophilic at that carbon, right? So if we look at our blue box, guess what that carbonyl is? Electrophilic. Okay? Well, that was kind of boring. That's the exact same thing. Why is Mike going through and saying we now add some structure, but now saying the chemistry is exactly the same?
Is it the same?
It's not the same. What's that? Why is that other carbon partially positive? And which carbon are you referring to?
I'm going to say the blue one.
The blue one. Oh, interesting. Might color coded even. There's a blue carbon. If you look really carefully, it's dark blue. but it is indeed blue.
We have resonance.
Do we have resonance? Yes. Yes, we have resonance causing that blue carbon to be a positive charge. And our alkene now becomes, yes, if we drew that out, so I'll accept that as a valid answer on this. Okay, so what Ylide is referencing is that we now have an enolate in there. Okay. But I'm addressing back to our alkene. So we're looking back at our starting structure. This pi bond now acts as what? That's a really weird phrasing. I should not be calling it a pi bond, because that might be misleading you. The carbons of that alkene can now act as the alkene is now acting as an electrophile. So that's not that big of a deal. Think back to all of the alkene reactions we did. And in all of the alkene reactions, what did they act as? Nucleophiles. They don't react as electrophiles. But the instant I drop that pi bond, that alkene next to the carbonyl oxygen is electronegative enough to withdraw the electron density, causing the carbons of the pi bond, of the alkene, to act as electrophiles. Neat. Okay. What makes that even worse, though? So now let's go back again to that blue box. We just said that carbonyl, being neat, is now partially positive. Or sorry, not the carbonyl. I have just given away the answer. The alkene carbon is partially positive.
The second partially positive.
The carbonyl is also partially positive. Which means just by bringing those two functional groups together, what has now happened? I have more reaction sites. I have two electrophiles. Which means when I add a nucleophile, I now have to make the decision, does the nucleophile attack the carbonyl, or does it attack the carbon? There's now a difference between them. That difference is going to come down to everybody's favorite, kinetics and thermodynamics. Okay? So, if we go through and look at how that modified structure reacts, if we add the strongest nucleophiles, strongest nucleophiles, because they are that strong, they need to get killed as fast as possible. So they are going to react with the absolute most positive thing. Well, which is more positive? The red carbonyl carbon, because it is closest to the electronegative oxygen. So if I throw the strongest nucleophiles at it, that's where they attack. What are my strongest nucleophiles that we have talked about? Sorry, say that. Yeah, I was afraid you were saying LDA. Not LDA. LDA is a base, not a nucleophile. It's too large to act as a nucleophile, so not LDA. God, I wonder if we had like a review slide that listed out all the stuff that we had just talked about. Oh, all the hydride nucleophiles? Yeah. Lithium aluminum hydride, sodium borohydride, all of them directly attack the carbonyl. Okay? They do not attack the carbon, our blue carbon, if we will, of our alkene. Those will all directly attack the carbon. Okay? Grignard reagents, okay, attack the carbonyl. Okay? Acetylides attack the carbonyl. Alkyl or the organolithium attack the carbonyl. Wittigs attack the carbonyl. Well, dang, Mike, you just talked about everything. Well, there are some other nucleophiles that are strong, like hydroxide. Hydroxide is a base or a nucleophile. That's negative, right? So that's still strong. That attacks the blue carbon. not the carbonyl carbon. Okay? So if we see strongest nucleophiles, hydrogen, carbon, go to the carbonyl. If we see oxygen or nitrogen, go to the carbon, okay, of our alkene, our blue carbon. Kind of make sense? Okay, so let's breathe a moment, because we just have to, like, cool, that's a nice rule that we just accept. Let's read the slide a little bit carefully here. Gilman, using RBR, what is R? What was it? What was R? You can say it louder. Carbon. Okay, with lithium. Well, that would make an organolithium reagent. So that would be a negative carbon. I didn't react that with copper. Oh, goody. But I have a negative carbon, and where does it attack? It attacked the blue. Just because we have a negative carbon does not mean it's strongest. The Gilman reagent is a new reagent that we'll be talking about that is an organocuprate. Okay, so it's an organic compound with copper involved in it. Okay, that weakens the negative nucleophilic carbon just enough that it doesn't attack the carbonyl, it attacks the carbon of the alkene. Okay? So there is a line there in our carbon reagents. Okay? Unfortunately, we just need to know what that line is. There isn't really anything we can do beyond just kind of being like estimating, well, I know it's less negative than that, but that's about it. There has to be a line somewhere, and it sits right above the Gilman reagents. Okay? Some naming on this. We said modified to conjugated. So we have the alkene next to the carbonyl. They're conjugated. That gave us the resonance, which is why the blue carbon became an electrophile, right? Okay? So we could refer to it as our conjugated carbonyl. Notice I had a hard time, well, it just attacks the carbon. Well, the carbon of the carbonyl or the carbon of the alkene, but it's not really an alkene. And there's two carbons of the alkene. That's just weird. So we have a new kind of name associated with these. You'll see them often referred to as alpha-beta unsaturated carbonyls. Okay, remember when we looked at the enols? We had a hydrogen there. We said that hydrogen was located at what position? The alpha position to the carbonyl. Okay. If I now add a beta, what happened? Well, that's alpha. To get beta, what do I need? I need another bond, and I now have my beta. Okay, so alpha, beta, we're referencing the positions to the carbonyl, unsaturated. What does unsaturated mean? What does saturated mean? Because that wasn't rapid fire enough questions. What have I now shown? Saturated or unsaturated?
Saturated.
Saturated, okay, so you know what saturated means. What is saturated?
Fully bonded.
No,
The octets not full.
the octets are definitely full on the alpha and beta position.
Yeah.
We could look at sp3. Okay, the carbons are sp3. They have all of their bonds to different atoms. Okay, it's fully saturated. It is typically in reference to the hydrogens. We've put on as many hydrogens as we physically can. So that is now saturated. To make it unsaturated, what did I do? I removed some hydrogens, but then that would destroy the octet on the carbon, so what also happens?
Added a pi bond.
I have to add a pi bond. So when referring to alpha-beta unsaturated carbonyls, that's what happens. We find our carbonyl as our 0 point. The first carbon is alpha. The next carbon is beta. If there's a pi bond there, that is now an alpha-beta unsaturated carbonyl. That chemistry is important because we now have an extra electrophile, right? Okay, so we have to be able to be cognizant and think of that chemistry. So, there's our carbonyl. We got some kind of prettying pictures of this. It's effectively inventing a new functional group. Okay? And everybody goes, oh my God, I can't believe there's a new function. Well, we didn't really name it, sort of. Okay, it is officially an alpha-beta unsaturated carbonyl. Okay, that's a big mouthful. And we have done it before, right? Like if I took, I don't know, a carbonyl and an alcohol, and I move them close enough to each other, what happens? Do I have a carbonyl and an alcohol anymore? Everybody's looking at me funny, so let me draw that prettier. What do I now have? I have a carboxylic acid. So the instant I bring two functional groups near each other, I change the chemistry of those individual functional groups. Okay? A carbonyl in and of itself is relatively electrophilic at that carbon. Okay? The alcohol, okay, mildly acidic. When I make a carboxylic acid, what happens? That becomes really acidic. What happens to the electrophilic characteristics? Becomes mildly electrophilic. Okay? So the chemistry changes as we bring in other functional groups based off of electronegativity and size and all those fun pieces. Okay? You've been seeing this throughout the semester, and that was what happened in first semester too. We're just trying to build on this. Okay? So, other terms that come into this, you'll hear reference as direct addition, okay, known as 1,2. 1,2, 1,2. That just wasn't funny. It's okay. So in a 1,2 direct addition, we're adding directly to the carbon and the oxygen of the carbonyl. So if I did a direct addition with, say, a Grignard reagent, go ahead and just make those not exceeding the octet. And we added a CH3 MgBr, right? We got a negative carbon. What happens? Attacks. Well, that just looks like I just added one thing, right? Why is that a 1,2? There's a second step. What's the second step in a Grignard reaction? Other way around. We'll add HCl to give us our alcohol. So in the addition, I added a hydrogen and a carbon. Those atoms were added at arbitrarily position 1, and once I establish one position, the next position by definition is 2. So I've got a 1,2 direct addition because I've added directly to the highest order functional group. What happens if I now make it a Grignard, or sorry, not Grignard, an alpha-beta unsaturated carbonyl? Okay. Now if I go through and add, say, like hydroxide, okay, I've only added it the one position, if we will, right? It's saying I also need to add at the 4 position. Well, what do we follow our reaction up with? An acid. This was a horrible example, by the way, but it gets at the idea. What did we add? Well, I added to the 1, 2, 3, 4 position, and I've done a 1,4 conjugate addition. Okay? Because we're infamous for, because it's your fault, that we're infamous for cliffhangers. What functional group is that? It's an enol. Officially, where this reaction ends is here, where the hydrogen was then added to this position. Okay? This is why when students look at the conjugate 1,4 addition, they're like, that makes no sense, because when I look at the product, where did I add things? the 1,2 position. I didn't add them at the 1,2. I added them at the 1,4. It's just the SOB of a molecule decided to rearrange to make it look like it was a 1,2. Okay? It's still officially a 1,4. Okay? The intermediate is what's showing the 1,4 addition. Okay? So you got to be careful on our 1,4 additions for that reason. Okay? That's the basics behind the 1,4. Well, I would love to continue to talk. I do kind of need to stop.